Hello, curious person, and welcome to my channel. Today we will look back at an old project of mine involving a special way of imaging cosmic rays. What you are about to see are unique images of cosmic rays. This is not a cloud chamber. These cosmic rays are moving in a solid. Nothing like this can be seen on YouTube. For untrained eyes, these images are just small curved lines, but they show motion of the ray inside fibers, actually bumping into atoms. Once you understand this, you will appreciate the beauty and detail of these images. This experiment took place several years ago, using older computers and camera equipment. It used an active scintillating fiber optic block and image intensification system. It will be described in more detail later on. Looking back, these old images are still awesome and cannot be found anywhere else. Shown below is an example of a nearly vertical cosmic ray entering the image from the top. The trace appears slightly curved because of the optical lenses. The white dots along the trail are interactions with atoms in the glass fiber. Another example below is a cosmic ray entering from the top center. It has a collision with an atom and causes an electron to fly off on a separate path. There will be many more images later on. This video is divided into 3 parts: Introduction to cosmic rays, Imaging of cosmic rays with an active scintillating fiber optic block and image intensification system, and video output of the imaging system including captured still images of cosmic rays and their interactions.
Hitting Earth every second from all directions is a bombardment of invisible cosmic bullets. They penetrate our atmosphere, having serious effects on our planet. Cosmic rays, as we now call them, are the most powerful penetrating objects known to mankind. They have far greater energy than any that can be generated by the most powerful atom-smashing machines that engineers and scientists on Earth can build. The exact nature of cosmic rays was unknown until the 1930s. Even today, there is some mystery about their origin. Some believe that cosmic rays may be messages from exploding stars or even more powerful objects like spinning neutron stars, giant black holes, or colliding galaxies. Cosmic rays were thought to be gamma rays up to about 1930. Scientists like Arthur Compton noted that this radiation reacts with Earth's magnetic field, since radiation intensity is greater at the Earth's magnetic pole. Our magnetic field steers cosmic rays to the north and south poles, where they collide with gases in our atmosphere to produce auroras. In 1937, the muon particle was discovered in cosmic rays. It is commonly referred to as a terrestrial cosmic ray. In 1982, Sekido and Elliott gave the first correct explanation of cosmic rays. They are very energetic ionized atoms from space hitting the atmosphere. To summarize, cosmic rays are charged particles zooming through space. They are the primary particles consisting of mostly protons and other particles. When these particles hit the atmosphere and stop, they generate more particles, which are called secondary cosmic rays. At the Earth's surface, many of these particles are muons.
Now let's discuss the cosmic ray detector and capture system. It is an unusual particle detector and tracker based on scintillating glass fiber optic technology. It uses a coherent fiber optic block consisting of 1 million fiber waveguides containing terbium oxide in the glass. Scintillation light is transferred by total internal reflection to the surface of the block, where an image intensifier senses and amplifies the optical image. Let's take a closer look at this device in the next slide. When ionizing radiation, like a muon or high-speed electron, passes through the fiber optic block, scintillation light according to its path is produced. A fraction of this light, about 5%, is trapped by internal reflection and transmitted to the fiber end. One end of the block is pressed into contact with the input window of an image intensifier. The far end of the block is mirrored with aluminum to reflect light back to the image intensifier. The terbium scintillating light has a slow decay, several milliseconds, but high quantum efficiency. It produces light of wavelength 570 nanometers, which is a nice fit for the image intensifier photocathode. This block was designed to look for particle interactions in a particle accelerator. When placed in a beam of pions or protons, interactions are readily seen. For our purposes, this block is sensitive to cosmic ray muons and electrons. With this small volume, we can expect to see about 1 to 2 particles per minute. The next slide shows the overall arrangement of the experiment. Here is the layout of the system components. The terbium block is on the right. It is placed in contact with the input window of the image intensifier shown in the center. The image intensifier used here is a 3-stage Vero Generation 1 tube. It has a phosphor screen on the output window for viewing or capturing video. Unfortunately, the internal optical system produced pincushion distortion. Video was captured with a low light camera and recorded. To see how difficult it is to capture cosmic rays, we will now show a portion of a video we captured at full speed, 30 frames per second. It is very difficult to see them, but don't despair if you cannot see them. We have captured stills of many cosmic rays from videos such as this one. We will show them after this one is finished.